Good morning, good afternoon, good evening. I would like to give a talk on nanostructuring through electro-patterned conducting polymer and colloidally templated arrays. I'm with Oak Ridge National Laboratory and the University of Tennessee as Governor's Chair, Department of Chemical and Biomolecular Engineering, and with Case Western Reserve University. So most of our work deals with the interfacial chemistry, nanopatterning, nanostructured materials, synthesis of nanomaterials at interfaces. And as shown in these representative cover pages of our work, we work on applications based on molecular imprinted polymers, sensors, different types of memory devices, and arrays. I'm also editor-in-chief of MRS Communications. So I welcome your best contribution in research letters, rapid communications, and review articles in terms of prospective articles. So today we're going to talk about conducting polymers, organic semiconductors, which is in the form of materials that are able to have charge mobility by electron delocalization, different types of hopping, inter and intramolecular mechanisms resulting in devices such as display devices, LEDs, solar cells, photovoltaic devices, sensors, and actuators. And our contribution in this work is in the form of new material architectures where polymers can be made into ladder polymers, dendrimers, different types of precursor polymers, things that can go into various devices, as I previously mentioned, but also able to use them for film deposition, or in this case, electrodeposition. So we pioneered the use of the precursor polymer approach towards electropolymerization of conducting polymers based on inter and intramolecular cross-linking, where a conducting polymer can be populated with electropolymerizable side groups and deposited as films. So one of our initial work was to actually demonstrate that this approach is viable for controlling the work function match with the ITO and the polymer layers to various redox states of, let's say, a whole transport material such as PVK. Upon completing this device using polyfluorine as a light emitting material, we demonstrated that changing the redox behavior of the PVK resulted in various turn on voltages. Not only are we able to do this in terms of the device configuration, but they can be also used to smooth the surfaces of important electrodes such as ITO or indium tin oxide. As shown here, ITO is actually rough with asperites, but this can be smoothed by grafting a polymer brush, let's say using the surface initiated polymerization approach as shown here, where vinyl carbazole was polymerized using an AIBN-like initiator. The result is a homogeneous film as shown by the AFM micrograph, where the smooth film serves as a whole transport material to complete a device. And so we demonstrated a similar configuration as the previous device. In this case, a PVK brush that was cross-linked electrochemically produced a lower turn-on voltage as shown here compared to a native ITO. By inverting the function, we can then use this configuration where the polythiophene PCBM is your active layer. In this case, in comparison to P.PSS, the PVK brush can then serve as an important layer to facilitate photovoltaic device performance. So in this case, the efficient device was shown in this junction bulk heterojunction type of system where the smooth curves in the film as well as the electrochemical cross-linking resulted in the performance, if not the same or better than P.PSS. So this means that from films, one can go to patterning approaches where lithography, mass lithography, electron beam lithography can be used to specific resolution, molecular imprinted techniques as shown later, as well as deep and nanolithography can be utilized to produce specific patterns using the electrochemical approach. In this case, a micro dot pattern was prepared by micro contact printing, where the electro deposition of a polyfluorine precursor was facilitated electrochemically with very clean lines and patterns, as shown this selective deposition on the dots, resulting in, let's say, a micro LED device. In fact, this can be carried all the way to nano patterning by utilizing the AFM tip as a electrode or a device that produces a bias voltage between, let's say, a gold coated substrate or conducting silicon. So in this case, the polymer precursor film is simply deposited by spin coating or grafting or deposition using polyelectrolyte layer by layer methods, as I'll show soon, where patterns can be made with high resolution all the way to less than 100 nanometer. This approach actually resulted in the ability to control these pattern features based on the amount of voltage applied, the residence time of the tip or current, as well as the thickness and properties of the film for cross-linking. So in this case, we were able to develop devices for sensors, memory devices, demonstrate nanoelectronics, and NEMS. In one particular example, we utilized the layer by layer approach to prepare films based on a polyelectrolyte or two polyelectrolytes that are oppositely charged, where the carbazole units can then be cross-linked to produce a cross-linked thermoset film. So the linear deposition of these alternating polyelectrolytes was tracked by UV-Vis spectroscopy, as shown here, with increasing absorption. This was followed by electropolymerization or electrochemical cross-linking to produce a thermoset film. But instead of making a film, we utilized an AFM to produce a pattern. And patterning was very easy. Again, applying the principle of the bias voltage on the surface, the electrochemical cross-linking was facilitated by the movement of the tip. The result is we can control the pattern, the features based on height, width. It's definitely the different movement of the AFM tip to produce this pattern. So this is a close work between these two graduate students, and in fact, after this work, they got the cover page in macromolecules and at the same time got married. Lastly, I'm going to demonstrate what we have done with electrochemical patterning based on colloidally templated arrays. So in this case, if you take polystyrene colloidal particles, let's say 500 nanometers, and deposit them in a Langmuir-Blodgett film-like deposition, one can create closely hexagonally packed arrays as shown here, where the template patterns can serve as a template for electrodeposition of a conducting polymer. In this case, polypyrrole was electrodeposited potentiostatically, as shown here, where a half dome, full dome coverage results in beehive or full dome structures or capsules, and removal of the polystyrene by dissolution, let's say in tetrahydrofuran solvent, resulted in this pattern. In fact, one can harvest these patterns as well, as shown here. So the arrays can definitely be used for electropolymerizing and depositing and patterning polythiophene, polypyrroles, polycarboles. In this case, we can take this bifunctional polycarbazole and deposit them on the surface, resulting in a pattern where removal of the conducting polymer results in a beehive-like structure as shown here. So this is an chemically deposited conducting polycarbazole on the surface of ITO or gold. We can then utilize the space inside those or the holes by depositing, let's say, a self-assembled monolayer film of macro-initiator polymers, where the macro-initiator for ATRP polymerization was first grafted on the surface, followed by grafting a poly-NIPAM or poly-N-isopropyl acrylamide brush, as shown here. So this resulted in lines and a height profile representing that of the grafted brush. This was better seen by differentiating them with the topography versus the conducting AFM image, where the green pattern represents that of the conducting polymer, and then the blue pattern represents that of the polymer brush. So you can take this approach and create polymer macroinitiators that are in fact electrochemically deposited uh, on the surface, showing this pattern here. But instead of utilizing this simply as a conducting polymer, we can actually grow a brush on top of these patterns. So these are macro initiators for ATRP, raft, and metathesis polymerization, resulting after the polymerization, let's say, of polystyrene in a polymer brush configuration as shown here by AFM. And again, since the holes are vacant, we can fill this or backfill this with an ADRP self-assembled monolayer initiator to create a ternary or tricomposition film where two polymer brushes are grafted on the surface with the corresponding electropolymerizable conducting polymer array. Now, to demonstrate the utility of these patterns, we first look at the membrane transport or diffusion properties of molecular ion probes, in this case, by demonstrating cyclic voltammogram, let's say with hexafluorophosphate ions and HCl ions, we can see that the ITO, by ITO, has a redox wave which has a large area of diffusion, followed by the control and different thicknesses of the polymer brushes. So the production of the array or the thickness of the brush showed that thicker films resulted in the tightening or limiting the diffusion to the substrate surface of those ion probes. And in a final experiment or demonstration, we utilize this approach to create molecularly imprinted sensors for chiral sensing of norepinephrine drugs. The two enantiomers are chirally opposite or mirror images. So a complex was first formed in an approach that we've detailed in many papers, where polythiophene was used as the monomer to complex with the norepinephrine in this manner, and then electrodepositing this complex electrochemically on these arrays to result in a patterned array. So these are sensor patterned arrays that were then deposited on a quartz crystal microbalance electrode. This QCM sensor can then be used to track frequency changes to differentiate the two enantiomers. And indeed, the chiral selectivity was shown by changing the templates on the two analogs, or selectivity based on two different templates. So we can differentiate between the two enantiomers or between different templates, and then finally capitalize on various approach of optimizing the deposition method as well to produce highly sensitive and selective films. So with that, I'll be happy to end the talk. Thank you, and be happy to take any questions.